So as we do every week, we're going to recap what we did last week in reinforcement learning and forecast what we're doing this week in neural networks. Last week, we looked at reinforcement learning, and we saw that the idea of getting occasional rewards to guide our process could be framed as a Markov decision process, where we built up from a Markov chain to a Markov reward process, and finally adding in actions that the agent can do to result in a decision process. And the Markov decision process is basically a fully specified environment where everything is fully observable. We can actually generalize this to a partially observable environment where we have to explore, and that's the setting for learning in the sense of reinforcement learning. We saw that the Bellman equations are a way of recursively looking at the form of calculating both rewards and state values, both state values as well as action values, right? Ones that are tied to a queue, which is basically specifying both a state and an action. We saw how this diagram at the end of our lecture embodies what we're talking about, where we saw that we have an environment that emits an observation and a reward, and then the agent has to decide what to do. In the case of a model-free algorithm, which is illustrated by the inner loop, by Q-learning, we have a case where the agent doesn't have a fully specified MDP and needs to explore to try to recover information about the transition function P as well as the reward function R. Right? It does this through a delta function and a small r function. When we have a fully specified MDP, or when we can learn a sufficient amount of it, then we can switch to the idea of doing planning. We saw one algorithm for that is called value iteration, which is basically a simpler form of doing policy iteration. This week, we're going to look at neural networks. It's the first segue into deep learning, which will be our next lecture. We're going to describe the basic idea of what a neural network is in terms of its topology, which is combining the linear units that we know and love all the way back from week 4, and then explaining the topology of how those linear layers get composed with an activation function that is a nonlinear one that allows a more complex behavior to be engineered. We're going to name potential problems with neural networks that we might see, describe how a neural network can be trained so as to output a function that's closer to the desired supervised algorithm, name different neural network regularization techniques, and then, in our practical application that you'll see in the notebook, obtain experience constructing neural networks using PyTorch.